My bad. Gosh, right? So using logarithmic scales really allows us to see what's going on a lot better than if we just use units, right? Because if we just use units, the fact that the US is a lot higher than most of these other countries for most of this time period would make all of that data smush down, and we just kind of see what's going on here in the United States. Once you get a clearer picture of what's going on with these countries, you can kind of see a little bit of what we were talking about this morning, right? That some countries exhibit convergence and other countries exhibit divergence. So, for instance, look here at the United States and Argentina. Notice that there's divergence between the United States and Argentina. If we go back here in the 1800s, the US and Argentina were a lot closer together. Today, they're much farther apart, right? In fact, Argentina only has about a third of per capita GDP that the US does, despite the fact that we used to be very close. So that's a good example of how how divergence is happening. We can also see convergence here, for instance, between Japan and the United States, or between China and the United States, right? Japan's an interesting case because Japan did a lot of convergence in the 1950s and 1960s and 1970s, but since the 1970s, actually there's been divergence between the US and Japan. In other words, growth in Japan has been relatively flat and growth in the US has been higher. China, we see, as we talked about this morning, a huge era of divergence between China and the United States. But beginning really in the 1980s, we saw a remarkable convergence between China and the United States that appears to be still continuing today. So, once again, in this graph, you can kind of see a little bit the variety of growth experiences. It's not that obvious if you don't put this graph on a ratio scale, because if you don't put it on a ratio scale, things get too smushed, right? That's a technical term. Talking about convergence and divergence, here's another interesting use of the ratio scale. This is going to be a graph that we talk more about here over the next couple of days, but we'll kind of talk about it now and then we'll refer back to it a little bit later. But this is looking at, this is a common graph that's trying to look at the level of convergence or divergence that's happening between countries. So what's being graphed here? On this horizontal axis, this is looking at per capita GDP with the United States, okay? Notice that this is on a ratio scale though. So each of these is a doubling from 1/64th to 1/32nd to 1/16th to 1/8th to 1/4 to 1/2 to 1, okay? So these are fractions, but they can still be placed on a ratio scale. So this is looking at how rich the country was relative to the US, but back in 1960, okay? So how rich the country was relative to the US back in 1960. That's what's on the horizontal axis. Then on the vertical axis, it's how fast the country has grown since 1960. Okay, so this is how rich you were 60 years ago, and this is how fast you've grown since. What do we see? In general, there's a positive relationship between these. So what does that mean? Countries that were richer in 1960 in general have grown faster. Okay, let me say that again. Countries that were richer in 1960 have grown faster. Is that convergence or divergence? Somebody help me out here. Convergence or divergence?
Divergence.
Divergence. Thank you, Carson. Divergence, right? If you were richer and you've grown faster, what that means is that there's going to be bigger differences in income levels over time, right? And so, yeah, this graph is a graph of divergence. This says that in general, the way of the world has been divergence. Having said that, though, you can see here there's a lot of error in this. There's a lot of noise in this graph, right? I mean, it's not like all these countries are falling along this very straight line. We definitely see some countries that diverge. We definitely see some countries that converge. But if you kind of look at all the countries as a group, we really kind of are seeing divergence. And that's, I guess, a little depressing, right? A little depressing. Anyway, once again, much easier to see this if you can express it on a ratio scale. Here's another example. Right, we're talking about a lot of data visualization here. Here's another way, though, of looking what's happening across the incomes across the world. So what's going on in this graph? Once again, we have per capita GDP in the US, or I'm sorry, per capita GDP relative to the US. Once again, expressed as a ratio scale, where each one of these is a doubling, right? Each one of these is a doubling. So how rich you are relative to the United States. Now here is the share of the world's population. So this graph is not looking at it country by country. If we go back to this previous graph, notice that we're looking at per capita GDP country by country. This graph literally puts everybody in the world all together and says what share of the world's population is living at 1/128th of the US GDP, 1/64th of US GDP, 1/32nd of US GDP, 1/16th. So what we see in this graph is we see good news, because what was true in 1960? Look at 1960, the whole world was living at a farther to the left of this horizontal axis. It means living at a smaller share of US GDP. What's happened between 1960 and 2017? Notice how almost the entire world has shifted to the right, meaning the entire world is living at a higher fraction of US GDP than it did before. So that's good news. And what's really driven this is China and India, right? Because China and India are such a huge proportion of the world's population. Together, those two countries account for roughly about 1/3 of the world's population. The fact that China and India have gotten richer is the primary thing that's pushed, right, this income curve over to the right, right? Meaning that more people are living at a higher proportion of US income. However, don't get carried away, right? It's still true that about more than 40% of the world's population lives on less than 1/8 of US GDP. Okay, let me say that once again. More than 40% of the world's population lives on less than 1/8 amount of US GDP. So in other words, more than 40% of the world's population is living on less than $8,000 a year. Okay, so that helps put things in some perspective for us, hopefully, right? Is that, yeah, it is true that income levels have gone up, but let's not get carried away, right? People are still living at small fractions of the income that we live at here in the United States. So, all right. So one of the questions that you have on homework number 1 is ask you to kind of create your own ratio scale graph, right? Create your own ratio scale graph. In fact, I think the question I ask you to do is to recreate these two graphs, right? But instead of using per capita GDP, just use real GDP. Right? So use the level of GDP as opposed to per capita GDP. So get this graph where you have levels and transform it into a ratio scale. How do you do that in Excel? Well, there's really a couple of ways you can do it. One way is you could just take the logarithm of your data, okay? But really the easiest way to do it is just to click ratio scale, right? So, you know, this is, I mean, sometimes Excel makes it a little too simple for us, but you should be able to find with just a little bit of work that you can actually put any data in Excel on a ratio scale. And so put it on a ratio scale of 2, right? Because you're looking at doubling, and you should be able to create that graph without too much difficulty, right? Okay, so that's it for talking about ratio scales for right now. Let's talk a little bit about some other mathematical properties that we're going to use here in this class, because we're going to be using growth rates a lot. And so we should know some basic properties of growth rates. So first off, I want to give you 3 rules. And these are 3 rules that hopefully you already know. If you don't know, these would be great rules to commit to memory. If you've taken calculus, they're not even rules, they're just things that you can figure out on your own. But because we don't require calculus for this class, we just ask you to memorize these. But if you have a function here that is that involves dividing, what happens if you re-express that function in terms of growth rates? It becomes a subtractive function, right? So in other words, if z is equal to x divided by y, then what's the growth rate of z? Is equal to the growth rate of x minus the growth rate of y. What happens if z is equal to x times y? Well, then the growth rate of z is equal to the growth rate of x plus the growth rate of y. And then finally, what happens if you have an exponential function here? For instance, z is equal to x to the a power. Then what's the growth rate of z? It just becomes a times the growth rate of x. So in other words, a exponential relationship becomes a multiplicative relationship. How do you work back and forth between these? Well, this really involves taking the logarithms of your function and then taking the first derivative, right? If you take the log and the derivative, you turn a function that's in terms of levels into one that's in terms of growth rates, right? So taking logs and derivatives, you turn something in levels into growth rates. So if you've had calculus, that's probably pretty obvious to you. If you haven't had calculus, as I said, we're not requiring calculus for this class, but you will find these rules, the application of these rules then, very useful to you. So here's a table from 3.1 in your book, and you might want to just go through this on your own and make sure you understand some of these examples, right? So for instance, if the growth rate of x is 10%, the growth rate of y is 3%, what's the growth rate of x times y? Well, it's 10% plus 3% or 13%. What's the growth rate of x divided by y? Well, it's just subtracting the two. Right, what's the growth rate of x squared? Well, it's 2 times the growth rate of x, or 20%, right? And so, you know, I won't work through all these little examples here in our class, but you can go back and kind of test yourself on these. But all of these are really a simple application of these 3 rules, right? These are essentially the rules that we'll use to turn any linear relationship into a growth rate relationship. So let's do an example of this as a class. Okay. Okay, so I want to work with a function and turn this function that's written in terms of levels into one that's written in terms of growth rates. What function am I going to use? Well, I'm going to use a function here that we're going to use a lot in this class. For those of you who took principal or intermediate micro, you're familiar with this function. It's called the Cobb-Douglas production function. Okay, and I can tell which of you have had intermediate micro because I just saw a shiver run down a couple of your spines. So it's bringing back bad memories, right? What is the Cobb-Douglas production function? It's just a way to think about production. And Cobb-Douglas says output, right, Y, is really a function of three things. It's a function of A, K, and L. Okay? What is L? L is typically labor. K is capital. And A is some amorphous productivity, right? Something that captures how productive we are. And then Y, of course, is output. Okay? So the Cobb-Douglas production function has a number of useful functions or a number of useful properties. In fact, we'll talk about these tomorrow, right? But this is a commonly used production function in economics, right? And really what it's saying is pretty simple. It's saying that how do you get output? There's really only three ways that you get output. You have more labor, you have more capital, or you become better at doing what you're trying to do, right? Labor, capital, and productivity, right? Those are really the three ways that you produce more. So your level of output should be related to your level of productivity, your level of capital, and your level of labor, right? Now, notice though that this is written in terms of levels. The level of output is equal to the level of productivity, the level of capital, and the level of labor. What happens if we wanted to rewrite this in terms of growth rates? Okay, what does this look like in terms of growth rates? Let's use those three rules that I just gave you to figure out, right? So we want to figure out what is the growth rate of Y. What's the growth rate of Y? Well, it's A times all this stuff. That's a multiplicative relationship. So when we take a level relationship and turn it into a growth rate relationship, it just becomes the growth rate of A plus, right? What's this in terms of growth rates? Alpha times the growth rate of K, right? So when something's to an exponential power, when you turn it into a growth rate, it becomes multiplicative. And then finally, what's true about labor? It becomes 1 minus alpha times the growth rate of labor. So if we can express this more intuitively, what's this equation really saying? All right. let's go back to our original Cobb-Douglas production function. Output is a function of productivity, capital, and labor. So what's going to determine the growth rate of output? It's a weighted average of the growth rate of productivity, the growth rate of capital, and the growth rate of labor. What's the weighted average? The weighted average depends upon how big alpha and 1 minus alpha is. The growth rate of output is a weighted average of the growth rate of A, the growth rate of K, and the growth rate of L. I guess that makes sense, right? Actually, it would be surprising if that wasn't the case. It'd be very surprising if that wasn't the case. How fast we grow depends upon how fast productivity grows, how fast capital grows, and how fast population grows. Okay. These three things we are going to talk about a ton tomorrow. So tomorrow we're really going to shift gears. Instead of talking about data, which is really what we've talked about here for the last couple of days, we're going to begin to develop a theory as to why countries grow at different rates, right? We're going to develop a theory of growth as opposed to just describe the data of growth. And when we do that, we're going to use this Cobb-Douglas production function quite a bit and rely on the fact that growth likely comes from either A or K or L. In fact, one of the big things we want to do tomorrow is we want to say which of these three things is most important. Is A the most important? Is K the most important? Is L the most important, right? And so we want to develop a model that helps us think about which of these is the most important. So that's really going to be one of the big things we do in chapter 4, which is your primary reading for tomorrow. Okay. Okay. So anybody have any questions about any of the math of growth, using logarithms, ratio scales, moving between levels and growth rates? A number of the questions on your homework number 1 really ask you to do these kind of things, right? To practice doing these kind of things. And so, yeah, hopefully you can take a little bit of a look at that tonight, and then you can get some clarity on what you might have questions with. All right, before I let you go, there is one last small topic here that I want to talk about to finish up chapter 3, which is kind of the philosophical question, is growth good? Is growth good? Is economic growth something that society should be shooting for, right? Is it something that society should be shooting for? And I want to talk briefly about 3 critiques that people might mention as a way of saying that maybe growth is not such a good thing. A couple of years ago, I can't remember if this was 2 or 3 years ago, if any of you were on campus, but there's a group of people called basically the Zero Growth Society, and they're advocating for policies that would essentially put an end to growth. And their argument is, we have enough income and output we don't really need anymore. Growing past this point is really bad for society. And so we as a society should say, we're going to stop growing, and we're going to think more about how we allocate resources, and we're going to think more about doing less harm as opposed to continuing to grow. And so what were some of the complaints or some of the assertions of people who kind of believe that a zero growth society is something that we should be shooting for? One of them is the belief that economic growth hurts the environment. Okay? So, does economic growth hurt the environment? Well, I have to say, in general, I believe the answer is no. However, that's gotten more complicated here recently with global warming because global warming behaves by different rules than most forms of pollution, right? So let me back up here and say why why is there an argument that growth doesn't hurt the environment? Well, the thing is, some growth likely does hurt the environment. But what happens as you grow past a certain point? You begin to get rich enough to care about the environment, right? And so what we've seen in country after country is that in the early stages of growth, there almost always is some environmental degradation. Why? Because people are pretty poor. And their first thought is, how do I get enough to eat? But what happens is they begin to get richer. They begin to think, maybe I don't care just about how much I eat, but I'm also caring about what the quality of my air is, right? And so this idea is often referred to as the environmental Kuznets curve, which if any of you have taken environmental economics with Professor Faruqi, undoubtedly you've talked about this. And so here's the idea behind the environmental Kuznets curve. Down here in the horizontal axis, we have GDP per capita. And so what happens when you're poor and you begin to grow? Yes, undoubtedly you do some environmental damage, right? Because people don't have the time, the energy, or the resources to devote to doing things as environmentally conscious as they should. They're more interested in getting enough to eat and feeding their families, right? And cutting corners if they have to. And so what we tend to see during early stages of industrialization is that, yes, as you get richer, pollution and other forms of environmental degradation go up. But then what happens once you get to what we could call the happy point, right? The happy point is when people's incomes begin to get high enough that now they start to care about the quality of the air they breathe, of the water they drink. They start to care that there's no trees around. And as a result, as you get richer, people spend more and more money on trying to protect the environment. Okay, this is an environment or an empirical relationship that economists have hundreds, thousands probably of studies have looked into. And it's really a relationship that you find time and time again across different societies, across different periods of time. You tend to see this, inverted curve, right, of growth leading to pollution, environmental degradation, but then past a certain point, growth leading to an improvement in the environmental conditions. Where is this turning point? It's somewhere between $6,000 and $13,000 per capita GDP, right? So, where exactly this is depends upon different societies. But once you get in that $6,000 to $13,000 range, right, that's really where people's incomes are getting high enough that they begin to care about the environment around them. And so we've seen this time and time again. We've seen this in London, right? In London, the quality of London's air in 1850 was the same as the quality of Tokyo's air in 1960, which was the same as the quality of Shanghai's air in 2010, right? So, and all three of those countries were at roughly equivalent levels of economic development, right? What happened in all three of those places? Well, it's still happening in Shanghai, but in London and Japan, air quality improved dramatically past kind of the low point as income levels got higher and people made decisions that they were going to spend resources not just on increasing output, but also resources on protecting the environment, right? So today in the United States, if you look at airborne particulates, they are about 1% of our previous highs, right? Our highs in the early 1900s, airborne particulates are less than 1% of where our highs are, all right? And so, pretty much across the board, whether you're looking at air quality, water quality, metals in the soil, et cetera, you see pretty big improvements. And you will see improvements in China. When Ben and I were there last year, we definitely saw improvements in air quality in China. China's making huge investments in renewable resources and solar that, hopefully will allow them to do the same thing that London and Japan have done. Um, Now, what's the kind of big caveat to this environmental Kuznets curve? The big caveat to this is global warming, right? It's carbon pollution. And the reason why that's a big caveat is because the economics of carbon are so much different. When you talk about things like water pollution or air pollution, these are very local, right? So local pollution causes local costs. As a result, locals have big incentives to try to clean things up. But what is it about carbon? Carbon is not local, right? Carbon produced anywhere in the world leads to global effects everywhere in the world. And so what does that mean? It means that this is a much harder problem to solve because a lot of people want to free ride, right? In other words, they would love everybody else to clean up the problem and for them to do nothing. And the problem is if everybody else waits for everybody else to do something, then nobody does anything. You really need to get coordination between countries and between individuals to be able to do something about this. The problem is that coordination really requires a degree of political cooperation that doesn't really exist globally, at least not very well. And so that's the big problem with carbon, right? It's not the economics or the science in many ways. It's really the politics of it. Economists for, probably going on 30 years now have been big fans on what they would call a global carbon tax. And what's this global carbon tax? Everybody in the world would have to pay a similar tax based on how much carbon you produce. So everybody pays a tax based on how much carbon. And what do you do with that money? Whatever you want. You could actually refund the money back to people at the end of the year. The key, though, is that people begin to incorporate the costs of the carbon they produce in the decisions that they make. And so if you set the carbon tax appropriately, you begin to have society think about the global costs of the carbon that they produce. And hopefully you get closer to a situation where you would definitely get closer to a situation where we'd be producing less carbon so that the impact of global warming would be significantly less. Would such a global carbon tax be costly? No. I mean, at least according to economists, no. The best study that I've seen suggests that the cost of a global carbon tax is 0.05% of global GDP. All right, I'll say that again, 0.05% of global GDP. That is not very much. It's almost a rounding error. Why is it so low? The reason it's so low is that if you impose a carbon tax, what are people going to do? They will change their behavior, right? It will instantly make things like solar much more economically feasible. Technology, right? A lot of research and development will go into developing ways not to use solar. People will change their behavior. Maybe they'll fly less. Maybe they'll use electric cars, right? Whatever. And so, all the economic evidence is that this is actually not a particularly costly policy, particularly relative to the benefits that it would create. So economists are strongly on board about this. Who's not on board is politicians, right? And I have to say, as an economist, I really get tired of politicians lecturing, me and my fellow economists about how costly the economics of this when we do not agree. I mean, the economics profession, outside of, a few, I might call them cranks, but the economics profession says that there is a lot of evidence that the costs of such a carbon policy are way outweighed by the benefits of it. And yet we don't do anything because of politics, right? So anyway, listen, I do agree, right? It's changed. This has changed a little bit, right? If in most cases, economic growth is not necessarily a killer for the environment. But global warming has changed that calculus, right? And growth does become a very dangerous thing in terms of the impact on our global environment. But I'm not so sure if it's growth that's killing the environment or our inability to deal with the consequences of growth from a political perspective, right? I mean, I would actually argue that it's the politics that are more screwed up than the economics. Another criticism that the zero growth people have, the second criticism I want to talk about, is that growth is not really related to economic well-being. And I just have to say, I just don't think that's true. I don't think that the data supports that. As we talked about this morning, your level of GDP is related to a lot of measures of the economic well-being, such as health, life expectancy, education levels. I wanted to show you this one graph, if I can, from a recent paper. Shoot. Hold on one second, let me find it. Yeah. Okay, here it is. So this is a kind of a hard little graph to read, but once here on the horizontal axis, once again, we have a ratio scale, right? Or here they call it a log scale. This is real GDP per capita, right? And once again, each of these units is a doubling, right? And here is a measure of life satisfaction. And life satisfaction is really just based on a global survey. Psychologists go across the world and they survey people on different factors of how satisfied you are with your life. And for each of these countries, there's a little arrow. And what the little arrow is signifying is where these countries started on the life satisfaction and then where they ended up. So each of these countries, I believe there's at least 6 different surveys across time. So for 6 different years, what was their life satisfaction and what is their GDP, per capita GDP level? And what you see here is that for almost every one of these countries, the countries that have seen an increase in per capita real GDP have also seen an increase in reported life satisfaction. There's a couple of countries where this looks very flat. They're kind of hard to see in here. But there's a very strong tendency towards feeling more satisfied with your life and having higher per capita GDP. Now you might say life satisfaction, smatisfaction. I don't believe it. I don't believe that anybody ever tells you the truth about how satisfied they are. I might agree with that, but that's at least one piece of evidence, right? At least some people report being happier when they have higher income, right? And so, I think overall there's a lot of reason to think that, yeah, when we're richer, we're happier. It may not be always true for every single individual, and it might be subject to diminishing marginal returns, right? Like maybe more income can only buy you so much more happiness, but I think there's a pretty good argument to be made that it buys you some. The final criticism that a lot of people who don't believe in growth have talked about, and I'm just going to end with this, is that many people believe that all growth does is it leads to more inequality. In other words, when you grow, it's really the rich that get richer and the poor don't share in it. I would say 2 things to this. First off, that doesn't have to be true that when growth goes up, inequality gets worse. As we're going to talk a little bit later, throughout big parts of US history, we've actually seen growth without growing inequality, right? If we look at the 1950s, the 1960s, and the 1970s, that was a period of strong economic growth in the US in which everybody shared in it, right? Both poor, middle class, and rich people shared in it. What's happened here since the 1980s is that I think it is increasingly true that growth has mainly gone into the pockets of rich. In fact, I don't think so. I know it's true because we'll look at the data that suggests that it's true. I'm not sure that I'm blaming that on growth as much as I'm blaming it on some other things that have happened in the US economies. Some of them are based on policy, and some of them are based on not responding to the way that our economy have changed. But yes, I don't think it's true that more growth has to lead to inequality. We've seen periods of time where that's not the case. We've seen countries where that's not the case. And so, yeah, I think growth can be shared equally, but you need to do it. You need to make it more purposeful than we've done it in the U.S., where we really haven't made sharing growth in any way purposeful. Haven't made it really much of an objective of our policy here, particularly over the last 30 or 40 years. We also know that when income goes up, it also leads to increase in education, and education is one of the great ways that you create income for poor people. All right, and so I think that's the other problem about arguing for no growth is if you don't have growth, where are you going to get the money for more spending on education, which is one of the the powerful factors that rise people out of poverty. So I'll say, just in conclusion, I think on this I agree with your author that growth can be good. I won't say it's always good, right? Because of course, how exactly you do it is important. But to say that all growth is bad, I think is way, way, way too strong, right? Just as saying probably all growth is good is a little bit too strong. But in general, you won't be surprised to know that me and most economists think that growth is more good than it's bad, right? Particularly when you do it right. So, all right, I went a little bit past our time. Sorry about that. Get outside and get some sun, all right? Tomorrow, I will send you a link, but the main thing we're going to be doing tomorrow is talking about chapter 4, okay? So make sure you take a look at that. Make sure that you do some work on homework number 1, and then we will definitely set aside some class time tomorrow if you have some questions about any of the things that are going on homework number 1, okay? All right. Thanks, everyone. All right, have a good afternoon.
Hey, I was wondering if you could, since the first half of the session today didn't get recorded, could you potentially go back through the top part of your notes slowly, just so like I can check my notes when this recording gets posted?
Yeah, let me do that. I'm going to do that fairly quickly. Okay, more quickly than I did it the first time, because I actually have to go.
Yeah, I mean, you don't have to like say everything. I just wanted to like
right. No.
Make sure I got everything written down.
Yeah, and this is good because a couple people missed this afternoon, and it was a screw up. I don't know why that is the hardest thing for me to remember to start recording. But let's see, where were we? Okay, so where we began today's class is talking about the rule of 70, right? Mm-hmm. Because of compounding, small differences in growth rates lead to huge differences in income levels over time. Am I sharing the right thing, Ryan? Okay, good. So the rule of 70 says that if something's growing at G% a year, it doubles in size every 70 divided by G years, okay? So if something's growing at 1% a year, it doubles in size every 70 years. And if it's growing at 2% a year, it doubles in size every 35 years. And so one of the things that I did in class, let me fire my iPad here again. Is I worked through this little example of, let's say that we had two countries, country A and country B, who started off as rich as each other. They start off with each $100 of income. But country A is growing at 1%, and country B is growing at 2%. What's going to happen in 140 years? Notice that country A takes 70 years to double in size, right? Because they're growing at 1% a year. So they double once in 70 years, and again in another 70 years. 140 years from now, they're going to be at $400 income. But what about country B? They're growing at 2% a year. And so as a result, they double in size every 35 years. So in 35 years, they double to 200. Then in 70 years, they double to 400. 105 years, they double to 800, sorry. And in 140 years, they've doubled all the way up to 1,600. So note, now they're 4 times as rich as country A, simply by growing at 2% relative to 1%, okay? And so that's really to emphasize this point that I have written down here, that small differences in growth rates lead to huge differences in income levels over time. And the rule of 70 is just kind of a quick and easy way to kind of illustrate that, right? And so how do countries get rich? They get rich by growing a little bit faster, but growing over long periods of time, okay? That leads us to the logarithmic scale. And what is the logarithmic scale? The logarithmic scale is basically a way of visualizing data, particularly data that's growing exponentially, easier. So let's think about population growth here, right? Let's say that population growth is growing at 2% a year, and population currently is 6. Using the rule of 70, if its population is growing at 2% a year, how long is it going to take to double in size? It's going to take 35 years to double. So in other words, if we have a population of 6, where are we going to be in 35 years? We'll be at 12. Where will we be in another 35 years? 24. Where will we be in another 25 years? Or 35 years? 48. So we connect the dots there and we get an exponential growth, right? Constant growth leads to exploding levels over time because of compounding. But this becomes very difficult to observe if you have a lot of years, right? Because what happens is that the scale up here at the top begins to dwarf what's happening here at the bottom. I think I went back and showed you figure 3.1 from earlier, right? Look how you really can't tell anything that's happening for these first 1,800 years because the scale has gotten so big up here that it dwarfs all the small changes for most of human history, right? That's the problem with just using units on your scale. So what can we do instead of using units? Well, we can graph data using a ratio scale or a logarithmic scale. And so what we do here is on the vertical axis, instead of making the units constant, we make the scale constant or the ratio constant. So here, a click from here to here is a doubling, right? So moving from 6 to 12 is one doubling. Moving from 12 to 24 is another doubling. Moving from 24 to 48 is another doubling. So the units are not constant, but the ratio is constant. When you do that, notice that this makes the trend linear. So it's a lot easier to see what the constant trend is, right? And so as I have here, really putting things in ratios or in a logarithmic scale really has 3 big advantages. It's easier to see what the trend is and easier to see that the trend is constant. It's easier to see variations from trend, right? It's easier to see variations from trend. I'll talk about that here in a minute. And then it doesn't distort the scale over long periods of time, right? So if you have big observations at the end and small observations at the beginning, the scale isn't so distorted that you can't see what's going on. So I talked about a couple of graphs using ratio scales. But before I do that, let's just look at an old-fashioned graph here of just units. Here's per capita GDP in the US, just in units. And notice that it's really kind of hard to see what's going on here in this graph. Early observations are very hard to see. It's hard to see ups and downs here because these units are much, much smaller at the beginning than the units at the end are. And so a lot of this data is kind of smushed down at the bottom, and it's hard to see how constant trend is because there's a lot of little ups and downs. So what happens if you put this on a ratio scale? Well, once again, instead of the units being constant, now it's the ratio being constant. Each one of these clicks is a doubling of per capita GDP. When you do that, a couple of things become apparent. First off, it's a lot easier to see how linear the trend is, how constant trend is in the United States, right? So it looks much more like a straight line. You can see how well a straight line fits the data, right? How well constant trend fits this data. The other thing is you can see much more clearly the ups and downs here at the beginning of the period, right? Because what this has done is it's kind of expanded the data at the top and smushed the data down a little bit at the bottom, making it easier to see what's going on. And so that's why a logarithmic scale is so much so useful in visualizing data over long periods of time. Here's another example of where a logarithmic scale is really useful, and that's looking across countries. Ordinarily, if you put this graph and you just, instead of using a logarithmic scale, you just use units, what you'd see is that the poor countries, all their data would be just kind of squished at the bottom, and all you could see is kind of the rich countries up at the top, right? The United States and the UK, and to some extent Argentina. But other countries that are much poorer, their data would just be squished at the bottom. By putting in a ratio scale, where once again, each one of these clicks is a doubling, you expand the data and make it a lot easier to see what's going on. And so one of the things you can observe here is that we see convergence among some countries and divergence among other countries, right? So for instance, China and Japan have kind of converged with the United States, but we see Argentina and South Africa have diverged with the United States. And so this is a lot easier to see when you look at data in a ratio scale. And then, Ryan, do you remember, this is where I remembered that I wasn't recording. I think this is where I remember where I wasn't recording.
It was right after this, yeah.
Well, right after this, okay, thank you, Cole. And so this is looking at a similar sort of scale, where here we have the ratio scale, but the ratio scale is as a fraction of US income. So whether the country is 1/64th of US income, 1/32nd, 1/16th, 1/8th, right? So doubling each of these. And on this axis, we're looking at how fast the country has grown since 1960, okay? So I think I said this wrong. This is looking at how rich the country was relative to the US in 1960 versus how fast the country has grown since 1960. And so what do we see here? In general, countries that were richer in 1960 have grown faster since 1960. That means there's divergence, right? That the richer countries have grown faster, poorer countries have grown slower. Now, this relationship is obviously not perfect, and there's a lot of noise and a lot of error in that. But we can kind of see where that's happened, right? Where divergence has generally happened. But of course, that's not all bad news, because this is looking at per capita GDP per country. In this next graph, which is where I picked up, we talked about it not as on a per country basis, but as an individual basis, right? Where do individuals fall relative to the US? And there we see more good news. So, okay, I think that gets us to where I screwed up. That was a good idea, Ryan. Thank you for suggesting it.
Thank you.
Okay, have a good one. Okay.
I had a quick question, though, before you go.
Yeah,
So all the formulas and equations and symbols and everything, those are in our book, correct?
Yes.
That we can go back and reference to?
Yes, absolutely. I mean, I
I
can't
just want to make sure, because like since you said we weren't getting the notes or anything like that,
yeah,
I didn't want to ask during class. So as long as they're in the book, it doesn't really matter.
Your book is the notes. I mean, and
okay.
I'd say in this class, I probably stick closer to the book material than I do in almost any other class. So
okay. No, I just want to make sure, because my last memory of our class together was 8th block last year. So
yeah, that was a lifetime ago, Cole.
Yeah, it really does feel like things weren't that bad yet, I think.
Yeah, the good old days when only 500 people a day were dying because of COVID.
Yeah, it was a little different times. Seems like it's been a long year regardless, though.
It's been a long year. But
and then I also had a question, though. Do you remember our research projects we had to do for that for eighth block, there was a particular website you gave us to find the GDP information that you said you were in favor of rather than other
Uh,
sites.
the St. Louis Federal Reserve.
St. Louis Federal Reserve.
Right.
Okay, yep, that was it. I was trying to look through my notes from eighth block and I couldn't find where I wrote it down at, but nope, that was definitely it. Okay.
In fact, in your homework number 1, that's really where I'm referencing you to get GDP data. The link is to the FRAD.
Yep. I just knew you. I recall you saying last for eighth block you liked that particular site for the information.
Okay. All right. Take care, guys.